I believe other people they may join late. So first off, let me introduce our guest speaker, Mr. Andrew Dunn. Mr. Andrew Dunn, he's a energy solution consultancy, and he's been working in the all energy field for decades. And he's currently with FENECON. FENECON is an energy storage company from Germany. It also has a headquarters in Greenville. Um, Andrew has been working with many other companies, and also he's got his own consulting company, A3 Consultancy. He's been leading many projects, very interesting, that are very relevant to us. Something like it's the electric vehicle charging station metering, and also for the applications of battery storage. Particularly, this FENECON is a battery storage company. Has a lot of products and projects ongoing about the big battery storage application. And also, Andrew has other projects around ship electrification. So that's a very interesting topic as well. Because for the while we are talking about vehicle electrification. He's one step further, working on the ship electrification. So today he's going to introduce some topics around the battery application in the real world industrial problem. We thank you so much, Andrew, for your time to give us a seminar. Thank you. If you're ready, you can please start.
Very good. I think I'm ready. Is my audio coming through?
Yes.
All right, good. I'm not using a headset, so just let me know if anything is not coming through. One moment. Just
Yeah, it works perfectly.
okay, perfect. Okay, so welcome everyone. My name is Andrew Dunn, and this lecture is grounded in a lot of my field work. And the projects that we will look at related to automotive and distributed energy resources, they're real active, deployed by either FENECON USA or myself and or partners. So I have about 20 years in energy systems and the utility grid and distributed energy resources. My background is in applied physics and engineering. And I also have recently completed two master's programs that are related to energy and sustainability and public policy. And so really approaching this from a practicing perspective overall, not so much theory. And that's the idea. There's a lot of words here, and you can read through what's on the slides to gather some more information, but I'll be also kind of highlighting some key points on each slide. So specifically, FENECON USA deploys the types of systems that kind of will fall throughout this lecture: industrial size, battery, energy storage systems, and other types of microgrids. So the title of the lecture is Islands of Power, Grid Edge Systems, Hyperscale Loads, and the Infrastructure the Grid Can't Wait For. And I think that will come through. This isn't meant to be about a particular one particular thread or topic. It's about the convergence of all of the different trends that are happening right now and how it's practical around automotive engineering, and energy systems. So with that, I'll jump right in. All right, so this is what I'm going to cover. I'm going to go quickly. Okay, I'm going to highlight topics, speak to key talking points about them, and then I can share this afterwards. But again, it's meant to be a convergence of topics that makes things really relational, real world based, and not as much abstract theory based. Okay, so here, just take a minute to read this. All right, and so here we're looking at EVs being really a big part of what we're talking about this overall lecture. So not looking to everything really has to change around the vehicle. So automotive engineers here and similar will need to spend a lot of significant career time looking into grid edge infrastructure, whether you plan to or not. So even, it's, I'll spare the details of the auto industry, but inevitably everything around the vehicle is becoming more and more relevant, even if not talking about electric vehicles, even if liquid fuels or combustion engines or hybrid vehicles. The same things apply, but here we'll talk a lot about electric vehicles. Okay, so here I actually have laid out 6 different ways that automotive engineering skills really directly translate into the work around them in the grid edge. It's really relevant. So I hear to talk to people a lot about jobs and career and things that they're interested in, and so this may capture some of that. So same supply chain and chemistry and safety standards. It's not really a stretch, but looking at the energy infrastructure and automotive, thinking about that is somewhat new. So highlighting here, second life batteries are a place where automotive packs and their engineering and stationary battery energy storage systems engineering actually physically converge into one product and have been for quite a while. So that's showing up here. And there's some really interesting common threads that you may not be familiar with that we'll talk about throughout this presentation. That's one of them. All right. So here, looking more at the power grid perspective a little more, there's a map from the NERC showing how the U.S. Has elevated or high reliability risks. This is a map that's really great. There's been some work done related to it, some synthesis, but it's really fascinating to see kind of where we're at. And the idea is, so everything that is currently in interconnection queue in the U.S. is about equal to what's on the power grid right now in total. So we have quite a bit of a critical mass happening where we have so much need, so much reliability coming up. And then looking at the queues of interconnection of loads and generation, we're looking at needing to basically match that. And some of that data shows up here in the trends on the left about like data center growth and things like that you read about. But there's differences in what you read about in the news versus the interconnection queues versus how that relates to generation plus loads. But we want to highlight some of these things, just the high level points here as we go through. Okay, so here, getting into this, we'll look at the physics foundation of things, batteries, architecture, chemistry, life cycle engineering, and some safety standards. It's really supposed to be practically grounded, though. So not as much theory where there's a lot of words and details and numbers. Remember, think practical. Okay, so in this, you have the same cells and completely different design targets going into a lot of what's happening in battery storage or electrification, including automotive. EVs will optimize for energy density and crash safety usually, and the battery systems and stationary will optimize more for the cycle life and fire containment right now. So overall, the actual architecture will be very similar or identical in many cases, but the engineering is diverging when we look at those two different types of systems. Some of you may be familiar with that, but it's really important to highlight because of the world we're in today. So overall system integration will determine how a project would be successful, not just the cell chemistry as highlighted in the previous point. So it's an insight that sometimes in textbooks in engineering, it'd be harder to see, but that knowing about integration gets you past the hump of having to match chemistries without the uses of the battery or electrified products. Okay. So just a quick snapshot here of looking at different types of energy storage and power storage that can be used. And here again, it's just to cover high level topics because these are topics that sometimes people don't know as much about. So overall, lithium iron phosphate at the top here is generally won out in terms of the modern marketplace for overall safety and cycle life and energy density at the right scales. Solid state is the area where we're looking for a lot of change over automotive and things really coming into the market the next few years. We've definitely seen some good highlights from Toyota and Samsung, SDI, and others who are targeting delivering solid state. So that would really create more of a premium segment for EVs. And we're in a time now where it's actually happening. So it's pretty exciting there. Okay. So just thinking about some comparisons here, and grounding things in some practical reality. Okay, so making things a little more relevant here and getting into a little bit more of innovation and cutting edge. So FENECON USA, the business that I help operate out of Greenville, South Carolina, very close to Clemson, is actually navigating through what's called UL or underwriting laboratory certification pathways, because there's actually no precedent for taking a battery that has never been used, which is called a first life battery module. It's really frontier pioneering engineering that's happening, because no one has identified yet that about 2 to 5% of EV modules and packs that are going to go into EVs are actually set for surplus inventory on shelves. That's hundreds of megawatt hours or gigawatt hours of capacity that we could use for the grid and industrial applications, but they don't meet the UL requirements for stationary. So EV first life, which you see on the left, there's a surplus that's meant to go to waste. So what FENECON USA is doing, one of several things, is creating this dual pathway with UL, what's called UL 2580, also a similar one for battery storage called UL 9540, creating these certification pathways for doing EV first life battery modules for cars. And you can think about how much waste there would be. Otherwise, those modules or packs have to get shipped around the world or go into some other use where they aren't certified for safety. So they don't have a place in the market. It's a lot of waste. So something we work on. And another example is Moment Energy out of British Columbia has commercialized doing second life battery energy storage systems from EV packs, and they can make that cost effective and they'll last for 10 years or more. And there's other companies doing similar. That's really the model that Tesla has utilized as well in their using old second life auto packs for homes and stationary storage. So Moment Energy is another one doing that. The first life area is a new area, though, that you will not find much about. It's very fascinating, and it's a global trend that we're really pioneering here in the USA to eliminate waste and increase available resources. Hopefully that's a helpful background on a somewhat possibly new topic. So keeping going. All right, so there's going to be some slides that have a lot of words on them. Just spare yourself. You don't have to, don't try to read through all the words. There's usually a theme. So here it's safety standards. And the idea is every standard on this slide will likely become relevant at some point in your career, or could be. So there's critical insights around the UL, which we were talking about. There's a 2580 and a 9540 for different applications, auto or stationary battery storage. So they don't transfer back and forth. That's what we were just talking about. Really good to know about these topics because they're very much in the forefront of the industry of how to close the loop on some of this. Often the same tests are done, meant for different applications early in the life cycle of a cell or a module or pack for batteries. And they don't have the right boxes checked off or the right forms filled out, and therefore it can't meet the right certifications or requirements for the different uses. So another one here is NFPA 855, which is how local authorities or AHJs will have interpretation, and it could vary very, very significantly. And that's where your local county or jurisdiction helps to understand fire safety and stationary battery storage. I understand this is mostly about automotive as a focus there, but it's really important because of this transfer, and fire marshals are always involved or interested when battery storage and electric batteries are involved. And so it's good to know about this topic and these types of themes and types of standards. Good way to get progressed in a career or get a good engineering career started is to know a lot about standards, safety, certification, and really dig into some of that. Okay, so moving right along here, I'm going to jump through a couple of other topics, and what we'll do is we'll tie together what we've started talking about. This one's about automotive to infrastructure, the bridge there. Charging systems, EV charging, vehicles interacting with the grid, and some really more fun topics that I'll mention that you may not have anticipated hearing about. So let's go. So here it's just like an overview of EV charging ecosystems, somewhat, accurate, but not entirely comprehensive. Talks about discipline of EV charging station levels at level 1, level 2, and how they have the controls and protocols, DC fast charging, which is faster, and has different interfaces with the grid, and then larger scale charging at megawatt scale, which is a lot of power per port. And it's a commercial specification for trucks, like the big class 8 trucks. They're actually required to have that type of charging. And it's a substation scale engineering type endeavor when you're talking about megawatt charging, right? It's like setting up an entire community basically, or something like that. So entirely different areas here. And one theme is thinking about charging vehicles, and then you can have AC integrated charging also. And this is highly relevant for the automotive sector. We're like moving into a time now where everything's integrated more. And so in a vehicle, you previously had electrical and and AV, audio, video in this case, visual, and then other types of aspects. And they're often integrated separately or by different partners or providers. And we are in this world where everything inside the vehicle is starting to be looked at together as a system more, which many of you are probably familiar with. And also there's this onboard AC charging. Like you can read about the recent announcement that the Tesla Cybertruck is now also qualified to do AC charging back to the grid in California. It just got approved. But that's one where you have the charger on board on the vehicle, so it's AC charging from the grid. Okay, so this is just another twist on EV charging and overall dynamics there. When I get through this section, I'll pause in case there's any clarification points, and then at the end we can go through questions and discussion. Okay, so another slide with a lot of words here. I want to highlight a few key points then, and when I share this afterwards, it's worth reading through the notes. But this is about those charging systems, and what you can have is demand charges from the power grid and the utilities. They charge you higher at certain times. And so what can happen is it's common to look at using battery energy storage or other similar products for backing, providing a buffer, so that during the period where the grid charges high demand charges, which most power grids do, you can use the battery storage. And what it does is it has the battery, is very cost effective. It will pay back in like 2 to 5 years, maybe a little longer. So often those can be added into DC fast charging or designed with my little areas with DC fast charging, and it can help. It pays for itself. It's a way to have good revenue. And then also ISO 15118 allows you to do plug and charge and also vehicle to grid communication. It's a really good thing to look into. And that's a protocol layer where smart charging is really a commercially viable thing. So really good to look into, because it's one of these practical things where in the markets or for companies like I just mentioned with Tesla, ISO 15118 or similar will allow you to go in and make a lot more money through having these new technologies as an owner or fleet owner, and understanding how the charging works in a more advanced way. All right, it's not like the older styles of charging and protocols. So that ties in the DC fast charging some. And then overall, what you want to look at is the ability for the power to flow in both directions, which is common, but sometimes confusing, reasonably so. So for example, vehicle to home, V to H, is commercial today. Vehicle to grid, market participation, is the next frontier. It's held back a lot. It's not like if you read the announcement by Tesla about the Cybertruck, you wouldn't really think that vehicle to grid is like moving slow. But if it has to do with a utility, let me tell you, it's moving slow. And if it has to do with really, really big companies like automotive companies working with utilities, rest assured, it's moving slowly. No matter what the headlines read, those types of organizations move slowly because of risk. And so vehicle to grid is coming. But when you read about GM, Nissan, Hyundai, BYD, and these platforms where they're ready for vehicle to grid architecture, there's a bottleneck. Don't be misled by articles, white papers, and PR. It's not vehicle to grid yet in most cases. If you put it into a microgrid and wanted it to do advanced functionality, it wouldn't work. It would break. The protocols don't match. The cybersecurity is not there at all. And then there's definitely not a orchestration layer there. You can have a local orchestration, but not like district level orchestration, which is more how V2G and the power grid work. So hopefully that helps. Really cool topics here, though, that are at the forefront of what's going on in the utilities and the industry. Okay, so moving right along here, lots of words, which that means don't read. So by this point, so it's a software-defined architecture though. So what's cool here to read about later is that the engineering challenge is not really in hardware or a charger or a car. It's the software. And this is where it gets fun because knowing when vehicles depart this is stuff sometimes maybe you don't think about. So when vehicles leave the station or the house, or how loads get optimized, or the vehicle to grid and how those get put together and aggregated. So basically machine learning skills allow us to start planning for this. And where this is converging that's really fun is in autonomous vehicles and fleets. Okay, so you can really think about software for leaving the station or the home, load optimization, and aggregating vehicles for the grid. Well, when you have an autonomous fleet, this gets really interesting because machine learning directly applies because there are no drivers. Okay, so this is what's happening now. And so you can do managed charging to, again, like mitigate when they charge so you don't get those peak charges, or use batteries for charging. So you have different ways the energy is flowing, not necessarily flowing back to the grid yet, right? We're thinking about charging of fleets and how to make that work. And what I want to highlight is that autonomous vehicles and depots are, what I have learned, are the most prevalent market activity in 2026. So I know I have friends who work for really, really large companies who do, hundreds of millions or billions of dollars worth of activity for projects and, infrastructure, industry, or small projects or communities. And what I learned from one of them recently was that they have just this really giant influx of construction, which includes integration and engineering, of autonomous vehicle fleets that are hitting the ground in 2026. So this is actually happening right now. And you can imagine, this is like with data centers, how it will help progress some of the convergence of these complex technologies, making them more simple. Because complex doesn't have to mean difficult. It just means you have to, make it work together, right? Naturally. All right. So quick case study here. This is our location in Greenville, South Carolina for FENECON USA. And what we want to do is we'll combine a lot of these really cool things. We'll have a real container that includes old luxury vehicle auto modules that are first or second life. We have them ready to use, and we've resold a lot of them and helped test a lot of them. And so we'll use those, put them in a container this year, and deploy it at our building in Greenville. You can all come out and see it next semester maybe. And we'll have a DC fast charger right there. And so we work with the fire marshal and the AHJ to make sure that everything's processed with the right packets and safety standards. But otherwise, we will have a really great way to have project managers needing to know, what's needed to meet NFPA 855 AHJ standards. And it's just real practical examples of, if you want to do fast charging or EVs or AC charging or microgrids with DC fast charging and batteries, then this is basically the type of process that goes through. And let me tell you, there's a lot of engineers involved. There's a great need for more engineers working across this space, actually. Critical infrastructure, power systems, everything we're talking about, major gap in the industry right now. So, and maybe not talking to the fire marshal or the planning officials, but you can do that too if you want to. And so I guess let me pause here. We're going on 20-25 minutes. I've got a couple of other sections to cover, and we'll continue to not get into too much detail, but I guess I'll pause here to see if there's any questions or if we want to adjust the flow at all. And again, we can have some questions discussion at the end. And if we just want to, wrap up and come back together later with any questions, I absolutely will share this. So we're kind of taking a step, I would say, now from like right now or just previous to glimpsing right ahead. We're going to talk about more about these depots, and then also more about large loads. So starting here, if you have like a class 8 truck depot where the big trucks charge, they basically, again, use more power than a utility substation uses. And so the battery energy storage systems can be used there for managing it and backing it up. And it's really the only economical case to be able to have enough power to discharge when you need that much charging. So you need a lot of energy stored to be able to discharge fast for whatever those needs are. And then, and that's a very common theme. I wouldn't imagine, yes, the power grid can always provide the 100 truck depot with power. That may happen in some cases the first time. It will hardly ever happen in the second time they come around asking to add the second depot. And you have to have more power. So overall, for example, NREL has done a study looking in Georgia and Savannah, actually looking at drayage equipment, and looked at how they could basically cut about half of their overall peak demand. And that was saving hundreds of thousands of dollars there. And it's just a common theme there, looking at that combination of battery storage and fast charging. Okay, so for large loads and industrial loads, we want to look at how they're basically shaping the grid, reshaping the grid, and creating a more urgent need for battery storage and deployment. And some of these technologies we've been looking at. And here, basically, data centers and ports, like shipping ports, are some anchor examples. All right, so large industrial loads, areas like data centers or our large port environments, inland and shipping ports, actually. We look at these, and what you want to think about is how they relate to automotive and how they relate to mobility. And it's everywhere. And then what happens in and around a data center and those microgrids is highly relatable. And it's the themes are just overarching here. So, for example, in a data center, if we want to think about this area, and we haven't gotten into them as much before, and there's lots of different types of data centers, then the server racks where the GPUs are running inside of those data centers are basically similar to where the EV powertrain is on a vehicle, if you're familiar. So you have the density of the power there, and then thermal challenges that you come up with, which I hear about often, and then more like engineering going on overall. So automotive wise, this is relatable. And it's what we generally get well in automotive for electric vehicles, at least. And so it's transferable actually over to the data center world. And I can't overemphasize that I constantly hear about solutions that we need for distributed energy resources or the grid or electric vehicles. And people say, well, we will just do this in the data centers, because the data centers, they don't wait. They just use the solution that's safe and that works. So everything's being implemented for data centers, which is why this is relevant to look at together. So a single data center campus overall is really more load than a hyperscaler, I would say, is more than most cities. In Charleston here, for example, we have several hyperscalers out as you go inland, and those are the equivalent of having new cities. And the utilities are trying to scramble to do planning out for the next 5, 10, 15 years around that, right? So getting into some real world cases and making it more relatable. This is myself, and work that I have done has been related to a combination of looking at electrification and mobility and using different ways to integrate some of these technologies. That's what I do every day and what I did throughout my thesis process. And what I'm looking at here is ways to find how diesel emissions or other types of internal combustion engines have different health damages that are actually already monetized. And the DOT guidance already gives us ways to look at the economics around that. So what I do is do net present value economics assessments on what the differences are when you do different types of electrification or hybrid solutions versus diesel or internal combustion engines. And so I've looked at this at different port environments, looked at it for Memphis extensively along the Mississippi River in their port, and currently work with different ports around the US, including here in Charleston. And when we talk to ports about mitigating diesel and changing to electric, and then electric vehicles and electric charging for the boats, they also always want to talk about electrifying their vehicles on land and the drayage equipment. So it's like this very natural progression. If you ever have experienced something that's a very natural progression, I can't say anything more about how transitioning over to electrified infrastructure, electrified shipping when feasible, and electrified mobility and drayage around ports, all automotive related, is one foot in front of the other. Literally, it's a journey. what's grounding and humbling is knowing that it lasts for decades. So it's not about, worrying about getting started. It's about getting started and keeping going, because the process of doing the new technologies has to be one foot in front of the other, because there's costs associated. People have to pilot solutions and all of this. So we have barges and towboats and different types of boats moving around in the ports and along the rivers and the Mississippi River. Tens of thousands of those vehicles pumping diesel emissions out constantly. And now what's happening is people are replacing those with plug and play electric barges and towboats, which have quite the nice economic return, and eliminate a lot of the maintenance requirements. So it's just an example of how this transition is already happening, and where some of these heavy loads converge, where the data centers and ports are happening, and the shifts that are happening on the ground. All right. And from there, as we move to the edge of the grid more, we can look at how, like, so far we've talked about the transition to heavier loads within this framework around looking at the energy and power systems, the EV and the automotive and the battery energy storage aspects, and even how that applies to non-electrified mobility. Now we can look more at the actual edge of the grid and how that relates to how these systems work together. And again, the goal is grounding things in practicality. So grid edge systems, they're the engineering area and discipline that's connecting everything more and more. You'll see this shift. And it's where real systems level thinking is required, because you have power generation, you have battery storage, you have various loads, controls locally and across a environment, different types of communications and cybersecurity, and utility interfaces. Any one of those areas could be quite a lucrative career work to go into, but all of it can be encompassed in the field of engineering, or an area of like understanding and engineering. And so here I have a layout of just some of what can go into just a basic layout of an architecture. And it's showing an AC bus bar here in the middle. And I worked with DC situations a lot as well, direct current, but an AC bus is correct here for most grid connected microgrids. And I want to show here like how the grid edge connects to the charging and it connects to the automotive. All right, so they connect here through power inverters or PCS equipment, and then battery storage and DC fast charging will have their own internal DC buses, and then they manage their own power electronics. All right, so then you have this shared AC bus, and then the DC bus microgrids are existing for specialized applications, right, like I mentioned before. So overall, grid forming inverters are a really common topic here, not grid following, but grid forming, which are required for islanded operation. And that's a critical technology distinction for a lot of what's happening today. Is this big transition to grid forming and full capabilities to do a lot of the outcomes related to that type of technology. So important one to get into. But without getting into inverters too much exclusively, let's talk a little bit more about the two different ways that you'll read about and be hearing about different types of systems being connected to the grid, because it's moving more and more to the edge, and the grid edge is becoming a micro version of the power grid more in many cases with large loads. So behind the meter and off grid are different regulatory categories with different design constraints, and they vary in different regions. Behind the meter has a utility grid backing it up. Off grid is designed to have its own autonomy, no fallback or real backup. And that's common in different types of scenarios, but a lot of what we're seeing get built out on the grid today is looking at that. So the cost of a grid extension is like $30,000 to $150,000 a mile. So it's not cheap. So that is one of the reasons that locations can stand up their own power grid, or that other corporate or private companies can pay to build out the power grid, because building out the grid is expensive. So you're basically just replicating what the utility does and then managing that risk. And news alert here, if you read about it, the grid, the utilities, And definitely typical power electronics companies traditionally haven't been able to do a good job for reliability either, which is why these topics are so at the forefront today. All right, so this should get a little more fun, and then we'll start wrapping up and be able to go through any discussion. So I've highlighted some areas here. This is pretty exciting in the work that I've been able to do the last maybe the last 10 years mostly. Like my career has been about 20, and, in technical as well as mostly commercial business. But a lot of the last, I'd say 5 years to 10, I've worked extensively across utility ecosystems and some of the more advanced ecosystems in the world. Here we can look at some real case studies and different engineering and policy lessons, and each geography is really different. So for these grid edge systems, as well as different loads. And what this has emerged for me as is this fun experiment that I don't really have many people who are able or like to talk about in a comprehensive view. But it's like traveling regionally, and then you get to do the equivalent of like a little bit of what I call time travel, because each power grid and community and region has different things going on, and they're staged by time usually. You can see like what the impact is based on certain penetrations of certain types of technologies or electric vehicles or wind or solar or a lot of coal or whatever it is, nuclear, hydro. You see all these things, and there's case studies where they're prevalent or already in an advanced state. And that's how the time travel works. And then the regional nature of it is that they're different, but there's similarities. And you can talk and communicate across regions. And so these regions are some of the major ones. Also, India, Kazakhstan. I've mentioned Canada here, all of the U.S. There's just some really throughout Europe. There's a lot of really good work going on. I don't mention the Caribbean here, but definitely the Caribbean and Central America is a major area. But so what I want to highlight, you can read back through this later, but for each of these, there's a really cool thing happening. So what we're looking at for the area in the Philippines and other island regions is to take this, it's not a hardware thing, it's really looking at controls and bringing them to the market. So basically, a lot of the islands like the Philippines have been hit with typhoons and certain natural disasters that made them put diesel in place to be able to give resiliency. But also there's not a lot of redundancy there. And so what's happening now is the UK and other regions are funding for other parts of the world to transition away from diesel. And so FENECON isn't necessarily as involved in the project in the Philippines, but does a lot of work throughout Southeast Asia. I'm working on this project in the Philippines in a couple of different ways for like the EMS system, as well as the actual deployment. And we're literally taking all the universities and large islands and all the communities that are mostly just on a radial layout, sitting by themselves out at the edge of the grid on diesel, and switching them to solar and batteries, and then having the diesel just as a redundancy, which will never really run. And then you'll have, we're transitioning to renewables, aligning with policy there. And other than logistics and just making it all happen quickly, a lot of what they have for the e-bikes and motorcycles and the mobility around there will all be charged for the grid. So you imagine how that transition happens. It's really fascinating. Okay, Hawaii also is a small but quite the laboratory region case study for looking at a standard for island grid scale and microgrids. The people I've learned the most from about microgrids work in the Pacific Rim and around Hawaii, and they've been doing it as long as anyone. And so we have this solution for grid forming inverters that are being used to solve for a lot of what's needed at the islands, and then remote microgrid projects going on. And overall, Hawaii has a renewable portfolio that's saying that, the PUC and then will mandate procurement of certainty that will lock in more private investment around clean power and battery storage. But in Hawaii, we have seen this interesting evolution where there's a lot of EV charging and automotive that's electrified, but it's a small region, and it's hard to get regulatory reform and processes through sometimes while being aligned with local stakeholders and contractors, because it's a small market that gets a small amount of attention doing a lot of things, and a lot of businesses have trouble keeping up with that and really putting the right resources into it. So Hawaii is a very interesting advanced grid in that way. They're simultaneously trying to put out wildfires while advancing the power grid, but while managing stakeholder buy-in, which is actually a major issue there of not wanting to move, not wanting to move forward. So where the grid edge went first, some of the most fun work that I've been able to do has had to do with Australia. We had what's called the race to a million endpoints, which was all the biggest technology companies in the world mostly competing to connect and plan a process to integrate a million endpoints for a power grid to be manageable. And spoiler, we won. But it's really fun. There was a lot of really cool stuff happening. And across the different grids and regions in Australia, there's different needs overall. And so you might have different types of these smart grid forming inverters or systems that just need to be synchronized with the grid better. And what's interesting about Australia is that each region has different constraints and needs. That's one of the things that I learned. Similar to each state or region in Canada, you have different constraints already in the different regions of Australia. So if you pick a spot and you point to it in that utility grid in Australia, and you rank the issues of grid constraints or too many EVs, too many solar and batteries, whatever the problem is that they need to manage, it's different and they're ranked differently in each market, which means they actually have to prioritize those items first, which means that the groups are actually focused on different things. So you have to knock off these same types of topics in different orders, but you have to do it like it's an emergency. That's what's important about these case studies. You don't get to wait in Australia and Hawaii, and data centers don't wait either, remember? So South America is fun as well. It gives us a glimpse into what's happening overall. We've got projects that are facilitating off-grid charging, and a company that I work with a lot is called Azimuth International, and we have these sustainable surf resort communities that are being developed, bringing in renewable energy and the indigenous and tribal communities to help with the planning and integrating local ecosystems. So you can imagine like replicability of this, where you have big commercial developers and financiers who want to do sustainable communities that are tailored to the local region and culture. It's all electrified with renewable energy and clean for the local environment. And then we're looking to translate that out into other parts of the world. And you see similar like ground up infrastructure change happening in regions like Chile, Ecuador, I mentioned Kazakhstan, and throughout India. There's these different changes happening that are similar, where it's rooted in more sustainable and resilient infrastructure. And this is a really good example that we see here. All right, so the deployment is really starting to happen, but we'll learn about it in as a trailing, story typically. Okay, so Canada is another really, really good one. Sometimes we aren't aware of what's happening just to our north, or maybe you are, but it's cold, right? And there's a lot of issues with thermal, advantages with having the same engineering discipline for EVs with the cold weather range management. We have the issues of thermal advantages of LFP in that type of area is really a big thing for battery storage, going down to those negative 40 degrees Celsius temperatures in some regions. But what I would highlight here overall is the fact that Canada is also a proving ground for hundreds of remote communities that are similar to what I mentioned before. They're off-grid, and they're starting to transition away from the diesel, right? So they're getting attention slowly but surely. And you can think of the fact that previously, just like in maritime shipping and ports, isolated or off-grid communities or islands are at this point where the economics and the technology and the access are all happening finally to be able to transition. And it's happening just based on the ability for providers to get those services to the customers fast enough. So if you think about business and career work, these areas are areas where there's actually a lack of delivery of solutions work. Like, so you can just go form a business as an engineer and work with people learning how to deliver off-grid or reliability solutions to some of these types of stakeholders. And there's a giant gap in providing that information out to the end users. You have to do so with quality control and assurance, right? But just fuel movement is another area where these people get hit so hard. So they have to move fuel in by air or ship, right? So let's help with some of that. Let's make it less. It does not make sense if it's not entirely necessary. Okay, last few slides here. Just want to highlight here. Okay, so that was a lot of technology and market information. Now I'm going to argue that the economics are what drive most everything, right? And remember, the power companies and the automotive companies move slow, always, and they go backwards and forwards, and based on certain signals. So economics and grid integration are where projects will get built. Okay, economics and grid integration. So this is where engineers who understand the systems will really differentiate versus just understanding like just one piece of it. So let's look at how that works. So on this slide, you see how different revenue areas can impact infrastructure. And this applies for automotives and the vehicles. Those Tesla Cybertrucks, why do you think they want to discharge to the grid? Well, it's all this money. Why else would you waste a good battery? And we're talking to municipalities and tribal nations, and they have all their electric buses. What do you think they're interested in? They're interested in what the heck this chart would look like if they knew that it existed. And then they're interested in, does this apply in my territory or with my equipment? And it's hard to know the answers to those questions. And so what we'll look at is DC fast charging sites. For example, just use that example, charging for infrastructure for cars or trucks, buses. They can do peak shaving of the rates on the utilities. Then they can use grant money from the government, which is actually still flowing in from electric vehicles, even currently with the policy. We have different credits that are available for vehicles or infrastructure that have to be accessed. And then there's actually more reductions on demand charges that get added onto the bill. So peak shaving and demand charges. And then what's really cool about this, we can look at more is, displacing the fuel cost is one thing, and it can be really, really high in places like the Philippines and Canada. That makes it just a no-brainer right out of the gate. But then in other regions, like throughout the US, you look at how you can stack up some of these additional incentives and where it makes the most sense to deploy infrastructure. And people go and access sites or lease sites or find retailers or franchises to implement different types of solutions or work with partners and people who have portfolios of properties to implement these types of solutions. Okay. So a couple of more key points here, and then some kind of highlights to close out. I've got a few more slides, but is again, promise to not ask you to read all the words. So what we need to look at here that's really important is that when around 2022, we had these changes start coming into place from the IRA and other federal administration changes or federal policy changes that were still in place. And even though some of that has changed, some of it's stayed in place, especially around manufacturing. And so there's a 45X manufacturing credit that is where battery factories can be getting built, and that's impacting our markets here. And that's important for all aspects of the battery supply chain. And knowing about that policy is really important. It applies to how you can get a rate of return overall on the systems. So knowing about the different types of credits there and the impacts from the IRA. And then FERC Order 2022 is what's telling us that we can aggregate or bring together these distributed energy resources, DERs, and we can include the fleets of vehicles that are doing vehicle to grid, and we can use them in wholesale markets. Okay, so that creates this unlock where you have the whole regulatory framework so that you can have EVs and virtual power plants commercially viable. So think about fleets of buses and trucks that can discharge to the grid together and orchestrated and aggregated through the same software. Then think about a community where the community developer can lease to the homeowners new cars, and those cars have AC or DC vehicle to grid built in, and they can set up a virtual power plant for that community to discharge at certain times together and orchestrate. And then they can have those homeowners pay like a lease payment or similar for the vehicle when they move into the community, right? So that's what is just starting to happen from a commercial standpoint. But it's how this all comes together into one piece. Okay, so last section here, closing out. So this is where it gets important. So there's a process-based failure mode analysis here across governance and coordination. And it's not related to technology. It's not that you can make a mistake with technology or not understand technology. It's just that the technology is not meant to be that complicated. it's that the engineering curriculum programs sometimes will, but sometimes often won't teach about how the interconnection of how systems go into the grid can make them not even work. Like, so when you can have a big project, then you go to the utility and they'll tell you it costs $1 million to interconnect it. And so you say, I can no longer do that project. So it has nothing to do with technology. It has to do with the power grid. And then projects can have other factors that can really derail them. So you can study the grid and do different types of studies like ETAP studies and different types of analysis for charging infrastructure or other distributed energy resources. But this really highlights, interconnection, finance, incentives, logistics, lead times, permitting, authorities, and then the actual controls and integration creep. They're all very, very real. These are areas I've dug into quite a bit in my career and have an extensive amount of experience working through. All right, so the intelligence layer is where hardware. So take a step back here. This is the intelligence layer, and it's specific, and it's where hardware turns into a system, and where AI can be really this indispensable thing that's coming together in some of the work that I know some of us are working on professionally and in research. So AI is important to scale as we do this. All right, so let's look at how that connects. Okay, so again, the machine learning stack for autonomous vehicles path is everything. Estimation and prediction and optimization within certain real world constraints. Done a lot of work around that in fleet planning. It's a huge gap area that we're really leaning into now as an industry. And that relates to vehicles and mapping it to the battery dispatch and the EV fleet charging optimization, right? So I've dealt with this like on the Mississippi River with barges and towboats charging and eliminating diesel, but the same thing applies for automotive, for vehicles, trucks, buses. So Clemson Automotive engineers are really close to the AI energy boom, and more so than many, energy AI engineers, because you have the convergence of this world of automotive as well. So at the grid edge, we know that an inverter will need to be able to respond in a really, really fast way, in this grid forming way. And that's the same thing that we're going to need, the same type of real-time consistency that the autonomous vehicle systems are looking for. So it's another area where autonomous vehicles and sub-millisecond response on microgrids for reliability that's happening almost everywhere now are looking for the same outcomes. And that's not uncommon to have an area where the same outcomes are all of a sudden needed, and they would have been really advanced outcomes 5 years ago. All right, so I think 2 more slides here, and so we'll wrap up by the bottom of the hour, if not sooner. So I've got something laid out here that another way of like time travel, which can be a little more fun, which is if you are going through school or finishing school around 25 or 26, and then you're running out an arc of the next, through 2050 or so, then what we know is that there's already this commoditization of many, many things that are being bought and sold. And then what's being added is like this value around software and then integration. And that's an area I would really lean into. So engineers who are able to see the like vision around across boundaries with software and integration, and really how that works at scale and with utilities and agnostic to just one company or brand, that is really, really valuable from a practical standpoint, because you'll have the AI campuses, hyperscalers with gigawatts of load working like islanded microgrids like we've been looking at happening everywhere already. So these grid edge skills are exactly what will be needed everywhere. And there are very few people who would cover the range of what's in this deck. Okay, and you can see how there are actually very limited number of threads that connect these topics that are key to know. Okay, so last slides here. So here, if you look at battery and powertrain engineering, charging and infrastructure, grid and energy systems, and autonomy with the software included, these represent real talent shortages. All right, so you've got transferability and battery and powertrain. And then you've got charging and grid. Automotive engineers are very valuable. So surprise to anyone who didn't know that. And you can make yourself marketable and valuable, especially if you have a passion around any of those areas, right? There's a lot of growth, a lot of companies are getting quite a bit of investment from the AI boom or from just like more success. So then first and second life battery engineering also will require people who understand both automotive pack degradation and stationary battery systems. So nobody has really done that, right? So that's Moment Energy, Tesla. Tesla just doesn't tell you about it, right? They're not saying, oh, we're doing these secret things and we need to hire people with a secret talent. They already were doing it, but they're growing and they have new divisions. Okay, so in wrapping up here, what I want to leave with is that in engineering, in this energy transition, it's really valuable to be able to connect, to look at how connecting systems that are designed independently in different industries with different standards and different business models can be viewed kind of coherently together. And it's a bit of a step back approach, right? It's not knowing exactly what the number or the spec is. It's knowing how to step back and know how to pull the right book off the shelf to be able to show that, right? And this is a macro view of that. But the expertise is in the practical nature of it and solving for the patterns and some of this complexity, integrations, software, silos. All right, so I've got some discussion topics here. It's meant just, again, it can go out with the slides, but it's just looking at topics that feel free to read these questions. And, it's all about, thinking about how this applies in the real world. So even if we don't get into some of these now, it's good to see if I'm thinking about career trajectory or needs or skills gaps or talent gaps, I would be thinking about how that applies regionally or how it applies to certain people's goals or passions, not just like what's on the resume, right? Or have I taken the right courses for this or had the right intern? It's region, passion, place. So thank you. Hopefully that was a good presentation. Thanks for letting me eat up quite a bit of time. Hopefully it was it was informative and it was intentionally meant to span multiple topics and weave the continuous automotive engineering thread throughout, since I know that's the topic of choice here.
Yes, thank you so much. Thank you, Andrew. It's a really great talk, very insightful. And I like your quote, the last quote on the last second page. For student, do you have any question? If you have, please feel free to ask. You just unmute yourself. Feel free to ask.
And don't be shy. I love all questions or just general feedback, but no pressure either.
Hi, Andrew. Yeah, like Greg said, great presentation. Thanks. I was a little curious, towards the start, you mentioned a large amount of the batteries that are manufactured as first life for EV applications are just being shipped off and like are kind of like stored as surplus. I don't know if you could dive a little bit deeper into like the market forces that are driving this and or supply chain forces that are driving this. I found that pretty interesting.
Yeah, it's a lot because it's the FENECON. It's part of the FENECON story. So FENECON in Germany started in around 2010 doing residential and commercial batteries and solar in the agricultural areas of southern Germany, and then just expanded. And with the Russia-Ukraine conflict and war starting, their revenue and needs for batteries and microgrids around Europe really increased. And why that matters is at that time, the automotive company Fisker was, I think, going bankrupt, or they were at least like getting rid of all their assets. And so there was 4 GWh of new batteries that hadn't been used. And that was the first 4 GWh that FENECON bought in Europe. And they're being deployed in like virtual power plant or across Europe right now in containers. and they're being paired with the right inverters and PCS and all these things that we looked at in this deck that sometimes aren't done perfectly the first time. So, we have containers full of Fisker modules with the BMS and the right inverters there and being deployed. And so I'm giving you an example of deploying this stuff in Europe, and then other cases where you can deploy these first or second life battery modules or packs from autos based on meeting certain regulatory requirements. So that's Fisker and FENECON meeting any regulations that Europe would require. But for FENECON USA, we worked with different companies to look at the UL certification process. And so I'm gonna point out two things here that will help understand this a little more. One is that the UL process does exist to reuse the batteries for second life. So, like, without going back to the slide, it was showing like when the batteries are at 80% or less overall percentage of health, they're reused in second life, and that's what Tesla always did. I was involved with Tesla when we first launched the Tesla Powerwall 1 in California back like 15 years ago. And I remember how we learned about internally at the time that they were reused auto batteries. And it was really confusing because it was back then. And we definitely weren't, I wasn't thinking about it the way I am now. And it sounded okay. So they're doing second life still in stationary mostly. And that's what Moment Energy out of BC does. The important thing there is there is a UL process for that. If you look it up, it may be 1974. 1973 is the one for testing new modules and packs of cells. 1974 may be the one where you retest and recertify existing systems that are second life. The gap is in the first life. And I don't really know, our CEO out of Germany does a really good presentation on this, talking about first life modules and packs, second life modules and packs, and then what he calls zero life modules and packs, which I believe has to do with the planning and design and factory. Kind of like what GM and Redwood Energy and Redwood Materials are likely doing with some of their manufacturing in the U.S. If you look at that, I think they're tackling second life, possibly zero life, which again, dig in and research that if you want. And then first life is where this gap area is. They may be working on that some. The trick is that in the automotive space, typically there's a lot of safety and testing done on the cells and packs or module level, but it's not the same set of tests that's done for the 1973 for the cells and modules and packs that go into the stationary containers for UL testing. So you end up with these auto packs and modules that were never tested. And the auto companies don't want to have their packs and modules tested for stationary purposes. Typically insert the comment about GM and Redwood possibly doing that now. But better yet, and then I'm going to get to the point about the inventory on the shelf really quickly. Better yet, there's ways. I mentioned our 2500 level UL test that we're working through, one of our dual pathways. And we now have a working group. This is really exciting news, and it's one of the coolest things about FENECON really in the USA. There's a working group now that consists of most all of those big companies that I mentioned, and a lot of people interested in like not wasting battery parts. And they are trying to make it so that the 2500 level test that can be done on auto modules and packs would transfer over to the normal UL process for stationary and go into what's called a 9540 and a 9540A test for the system. And that alone wouldn't be the silver bullet to pull all those products off the inventory off the shelf before it needs to go to waste or shipped out. But there's that working group is also trying to make sure that there's some type of like protocol that says that as long as these modules and packs and cells were safely developed to auto industry standards, then we're going to check off all these boxes that are saying that as long as they are not used yet, then they can be used in stationary. So we're trying to solve for that in the UL process through the 2500 level test that exists for auto, or a new type of format of a test or a sheet that would say, this meets the requirements to use similar to 1973. But in the meantime, auto industries typically, feel free to find a way to dispute this, anyone, it'd be great. But typically it's like 2 to 5% existing inventory is on average the surplus of the modules and packs that they have for the cars that never gets used. So even if you have like a run rate, that's surplus. So, you'd install a certain amount every year or two, and then there would be surplus per year, not at the end of the years. And so that surplus is what the first life product is. And the goals, I think, for the auto industry, maybe in Europe, are like getting it down to 2 or 3%. And so if you want to have some fun, go research what types of packs and modules different companies use conservative numbers like 1 and 2%, and figure out how many megawatt hours or gigawatt hours they'll have in each region. And that's what we're trying to free up in the US, so we can use those modules and packs inside of the stationary containers readily. It's just stranded, resources there. And frankly, I don't really know what happens to them usually. I bet they get shipped. I think they get shipped to Asia. But I'm not sure. And I only say that because that's what a lot of leftover inventory and product, what happens to it. It either is waste or a product gets sold into parts of Asia.
Great, thank you. Any more questions? Let me ask you a question. I remember in one of the page you introduced your FENECON battery. You say that they have 10 string. Each string has 16 battery cells. Do you probably mean that within each string, those 16 cells are connecting in series? Then there's 10 strings connecting in parallel. Do you actually mean those kind of configuration?
I probably should check, because of the fact that it's actually using the auto architecture, the auto EV module pack architecture. And that, I would say, as indicated in this discussion and the last point, is very unique. It's really cool. Like, we basically have 2 containers that we've built with a very well-known auto company that manufactures in the US, and we are going to deploy them, but they don't have UL certification, which we just all learned about and talked about. And since they don't have UL certification, we have to safely install them at our site and at one other customer or research or demonstration site, possibly Clemson. And so I'll check on the architecture, because it varies depending on whether you have auto packs or modules or not.
Okay,
it's all different and it may be that I have something written that's either incorrect, or it's not indicative of what the whole system looks like. So I'll look. I know actually on that layout, the talk about the specs, I actually already changed it, I think twice, because I was trying to make it more accurate, but it's not our standard architecture.
Yeah, no worry. I just want to know the details. No worry.
Yeah, exactly. So that's what, yes, let's send me a follow-up, because I can add, we have a Clemson engineer who is on staff, who loves answering these types of questions. And the cool thing is, he knows how to answer the questions about the different types of systems. So you can see how this is relatable, because that's what he's had to get good at. And not many people in the US know these different topics. So it's good. Yeah, happy to answer that.
By the way, for those battery storage you built, like in FENECON, it's more than a megawatt hour. Then usually, how do you charge them? Do you only use grid power, or you use PVs, anything else?
Yeah, it can be almost anything: grid, solar PV, gensets. Like, there'll be power generation from a natural gas or a diesel generator sometimes, like we looked at. It's like the reverse of the islands, or you look at the island and the remote microgrids, and that answers the question. But now
but your FENECON only sell the battery. You don't sell anything else like PV. You don't sell those things.
Yeah, that's more like on the A3 consultancy side, as well as working with developer partners. We actually have to work with developer partners, because we can sell batteries, DC blocks, as well as AC integrated systems with energy management. But typically, a developer is working or with an EPC, an engineering and procurement and construction company, who's actually bidding the project and all of that. And so they would likely be bringing in like solar. I would give you really, really briefly here. There's two examples. One is an industrial site in Augusta, Georgia, where they make a really sustainable natural product for food. And we're doing like solar on all the carports and solar on a field next door, and then batteries for backup and infrastructure, and then using AI to optimize the planning and the implementation of it, and that EMS, the energy management system. And a similar one, and that's with partners. FENECON is not deploying the batteries there because our batteries are just starting to ship in Q3 of this year to sites. These projects are already ongoing, but it's within my group. And then another one is like the Columbia Airport. And there are similar airport microgrid work going on in the Greenville and Spartanburg airports. So it's really cool to think about this where you have batteries and then you have solar at many of the airports. And that's actually getting funding from the federal government, and the states are paying for a lot of that because they want the airports to be resilience hubs to have backup and not lose power.
Yeah, that's fantastic. Yeah, I think I will have one last question to ask for the students. Because currently we have quite a lot of international students. Every year they're looking for all kinds of intern opportunities. So if there's any incoming internship opportunities from FENECON or from any of your connection network, we really appreciate that you could let us know.
Absolutely. I will. Yeah, a lot of companies including battery manufacturing and also like microgrids and battery integration and deployment that I'm working with, like at least 3 or 4 different companies. So sometimes we don't post internships. So I think it's worth, like we've looked at before, like reaching out and, putting people in touch. But also if I have any internships available, I will definitely send those out to you all. And don't hesitate to reach out with any questions. Don't mind talking.
Okay, thank you. Thank you so much. I think it's end of the class now. We really appreciate your time, your great presentation. Let us thank Andrew again. Thank you so much. So in the end, I will need to talk to Aju after the seminar.
All right. Thanks, everyone. Have a good day.
Yeah, thank you so much.
Thanks, Jeff.
Take care. I need to talk to Andrew for Archie for his report. But everyone else, if you want to stay, just feel free. Still discussion continued from this Monday. Just to clarify the coding, the variable thing. Sorry, let me disable the recording so that it will not record it.